Today we are planning to discuss about the basic design philosophy involved in design of pre-engineered steel building structures. In the recent times, the construction of pre-engineered building structures have become very popular compared to the conventional steel structures. Very large amount of construction in this using this technique is being executed all over the country. In development of, it is helping a lot in the development of infrastructure and achieving a very good economy also. A well designed and constructed PEB structure would achieve economy. Construction will be done at a very low, comparatively lower cost, faster in construction, elegant in appearance, and maximum utility of the space constructed. All the functional aspects required by the client are taken care of without increasing the cost. But as far as the designer is concerned, the methodology and the standards used are same for a conventional steel structure as well as a PEB pre-engineered building structure. In both the cases, we are using IS 800 as a standard, and methodology is same in both the cases. But then what is the difference? The basic difference is in the philosophy being used in designing a PEB structure. Compared to the conventional steel structure, in PEB, very accurate design is done without leaving anything to imagination. All the loads are considered, all conditions of loading is considered, all possibilities are considered. These are possible because of the latest softwares, faster softwares are available. Optimization of material use at all levels so as to get the economy. Precise fabrication under controlled conditions of a factory so that the fabrication at site is minimized, and a very faster methods of erection. These are the reasons why the PEB has become popular in the recent times. But the catch is, when you are going for optimization, calculating the loads accurately and designing very precisely, it also requires very good knowledge, care, both during the design as well as during the construction. So we will go into the design philosophy. Compared to the conventional building structures, in pre-engineered building structures, we always go for a three-dimensional analysis. The reason is we want to take the advantage of all the members participating in resisting the forces, especially the lateral forces. Compared to the conventional steel structures which are using 250 MPa hot rolled sections such as I sections or angle irons or channels. In the case of PEB, we are using high strength MS plates having a strength of at least 345 MPa, 345 Newton per millimeter square, or even higher strength. Nowadays up to 400, 500 MPa steel plates are available and are being used. Then, as I told you, in the design philosophy, we always try to optimize the structural arrangements as well as optimize the cross-sectional area at every point in the structure so that the maximum economy is achieved. We use largest possible member length so that we are having minimum number of connections at site, and these are carried from the factory to the site in a fully fabricated form. We will go into the details of this. As I told you, in the design philosophy, the first and foremost is the design of the optimization of structural system. When you are modeling a steel structure, we can change the number of columns, we can change the number of frames, we can arrive at the most optimum structural system by which overall economy is achieved. Then optimization of the member sizes and shapes, very accurate load combinations, use of high strength steel, as I already told you, use of 3D analysis, consideration of erection loads very accurately, and full utilization of cross section of the members at every point, and deflection control achieved to the required levels only. Let us see how this is being achieved. Here I am showing you the structural arrangements generally used in a structural system generally used in a PEB structure. First one is a clear span. This type of structures with a single span can be used up to 75 meters economically, or maybe multi-span with one interior column or two interior columns or three interior columns. In all these cases, approximately the length of each span, each unsupported span may be limited within 70 meters. If it goes beyond 70 meters, it may become uneconomical. Now, first thing we will discuss about the optimization of the structural system. By deciding the spacing of portals, if you are increasing the spacing of the portal, the number of frames can be reduced, whereas then we will be getting higher unsupported length of the purlins and other secondary members, which may increase the cost. On the other side, if you are reducing the spacing of the portal, the purlin size may reduce, but we may be increasing on portal. So, by practice it has been found that 8 to 8.5 meter spacing between the frames, between the portals is generally economical. Where heavy crane loads are existing, bay length up to 12 meter may be economical, because column sizes maybe frame size will be very big. So, we can go up to 12 meter spacing of the portals. Second is reducing the column sizes by transferring the lateral loads to the inner portals by bracing. In a steel structure, when lateral loads such as wind loads are applied, the gable end portal will be receiving the maximum lateral load, resulting in a very heavy section. So, these lateral loads, in order to economize arrive at a better economic solution, we will be providing a good bracing system in such a way that there is lateral loads, the wind loads are transferred from the gable portal to the second portal or to the third portal even. So, by designing simple bracing system, this considerably we can reduce the size of the gable portal. So, this is shown in this picture, the transfer path. As you can see in this picture, the gable end portal is connected to the second portal using bracing both at the tie level as well as along the wall. Column bracing, roof bracing and tie bracings are given between the gable portal and the first portal, as you can see from the second picture. The third one is selection of the column support condition. We can make the column support condition as hinged or fixed or something in between also. It is generally found that fixed base connections are more economical for large spans greater than 25 meter or with heavy crane loads, and less than 25 meter pinned base connections would be economical. Or you may be able to need not be fully fixed or fully hinged. It can be partially released base connections also are possible. It depends on how you are placing your anchor bolts, how we are anchoring the column onto the base or the foundation. Pinned base supports also result in higher deflections of the portal, because when you are going for pin connection, naturally the size of the column will reduce, but then the deflection of the portal or the rafter at the center will be increasing. So, you have to, this is a give and take, you have to accordingly consider the amount of fixity at the base, so that we are maintaining the deflection at the center as well as achieving economic section. So, by such iterations or activities, an optimum structural system can be arrived at. Then number of pieces in each portal. This depends upon what is the maximum size of the portal piece or portal beam or the column which we can carry to the site. It depends upon so many factors, like it may be even depending upon the geography of the place or the infrastructure, road infrastructure available, vehicles available, size of the structure, amount of steel used in the structure, and capacity of the manufacturer also. In any case, try to make the pieces as big as possible, so that the connections at site can be reduced. More number of connections result in an uneconomical structure, more cost as well as more risk because the connections are made at site. Similarly, roof slope, generally a slope of 1:20 is considered as optimum in case of a general structure, but steeper slope is preferred in heavy rainfall or snowfall areas, and accordingly it can be designed. But then you can have iterations like whether 1:20 is optimum, or 1:50 is optimum, or 1:10 is optimum. This can be done by a few iterations. These are nowadays faster softwares are available, so this is not a big deal. You can arrive at optimization very easily. Then one more important thing in optimization of structural system is very accurate load calculations. The dead load including self-weight of the structure, all cladding material, even weight of the fasteners should be considered. Nothing should be left for imagination or approximation. Live load, all kinds of live load should be taken. All collateral loads, superimposed load due to cable, false ceiling, HVAC system, that is ventilation air conditioning systems, and anything else, whatever is supposed to come, superimposed loads which are considered in the structure, should be taken accurately and incorporated in the loading. Because if you are leaving something to imagination or something as arbitrary or random, then unnecessarily we will be putting a factor for that, and it will be increasing the cost for no reason. And for wind load, seismic loads, seismic loads are also to be taken very correctly. Snow loads, rain loads, crane loads, what kind of crane being used, all these things, all the loads to be taken into consideration, and all possible load combination as per IS code shall be taken. When you are designing a PEB, even if you are having a, even if with your experience, even if you feel that some of the load combinations are not significant, please don't leave that load combination. All possible load combinations given in the IS code shall be taken, because we are designing the structure very accurately, utilizing the sections to the maximum. So, yes, any error at this stage may result in a catastrophe. Now comes as optimization of section sizes. Now each section is to be optimized. It is very easy, it is possible because we are fabricating it out of the sheets. So it is not required to provide any extra length or thickness or width for a section more than what is required at that particular section. So tapered section sizes of various members of portal by matching with the stress pattern should be adopted, achieving the optimum weight. Whatever is minimum required shall be achieved. Sometimes we can use a thinner plate by using stiffeners, flange bracings, or flange and web bracing. So with this stiffeners, providing stiffeners very intelligently, providing the stiffeners at the right place, we would be able to save a lot of steel by reducing the thickness of the members, and we also will be reducing the dead weight of the structure. And as far as purlins are concerned, compared to the earlier conventional structures where channels were used, in the present PEBs we use Z section purlins. Generally 2 mm thick or 2.5 mm thick sheets are used and fabricated into an Z section and used as purlin. Always remember, if you want to have economy, even though this is a 2 mm section only, this overall, because number of purlins and guts are more, if you are not designing this properly, you will not be able to achieve proper economy. Always use a continuous beam design for purlin, not as a single piece. Design the purlin continuously. When you are designing the beam continuously, as shown in this figure on the right side, as you can see, the gable end, the first part of the purlin will be carrying a higher bending moment, and similarly at the supports, where the rafter support is there for the purlin, the bending moment will be much higher compared to the midspan. So if you are using a same section purlin throughout, then you will be providing this purlin for the highest bending moment. Thus at other places you will be providing unnecessarily thicker sections. So this can be corrected by providing overlaps at supports for higher support moments. As you can see in this picture again, on the left hand side, you can see that the purlin from the left side and right side are purposely overlapped over the rafter, so that the place where the bending moment is higher, two sections of purlins one over the other is available. This is possible because we are using the Z purlin. So, one Z purlin can be kept easily on the second Z purlin, so that at the support point twice the thickness is available. Similarly, at the end gable end purlin, instead of one purlin we will be putting two purlins, or we may even reduce the spacing of the purlin by providing one intermediate purlin between two purlins. So, if the purlin spacing is say 1.8 meter, 1.7 meter for other places, it will be 1.7 divided by 2 for the gable end bay. Then if you are using purlin length, this spacing of your frames are 6 meter, 8 meter, then naturally you have to use sag rods instead of using thicker and bigger purlin sections. Enough number of sag rods are used so that the stiffness of the purlins in the y direction can be compensated by using the sag rods. And inclined sag rods are provided at the ridge purlin as well as for the girt, that is the members used for fixing the wall sections. So, all these things together will help you in achieving the economy. So, this is a basic design philosophy as far as the design of PEB structures are concerned. Remember that a PEB structure will be economical only if you achieve this optimization intelligently using the technology without compromising the structural requirements. There are a lot of redundant, people generally tend to provide a lot of redundant members which are not required. This can be taken out, this can be tried. You can have a number of iterations using latest softwares and achieve the optimization. Then and then only the PEB will be an economical option compared to the conventional loan. That is all for this video. We will have a few more videos on PEB which will help you in executing PEB structures successfully.